about our European project Bots to Rack and some key findings that we made running a test-driven development process. So basically, it's how we came from concept to one of our latest prototypes here. The background and motivation for the project is asbestos is used in millions of flats in Europe throughout the years between 1950 and 1990 due to its advantageous properties, and it's used in many different areas like fire protection, insulation, or as supplementary components. During the time, also found out that asbestos can cause diseases as asbestosis, and that it is probably increasing the risk of lung cancer. This all resulting in banning asbestos by legal channels. So in the late 1990s and early 2000 years, asbestos was banned from the European construction market. And all this together means we have a lot of flats in Europe. We are not allowed to have it anymore. So there is a use case for refurbishment. And there's also a special kind of refurbishment because due to high regulation standards that we need to face because we are handling hazardous elements. And what we saw was that the use case of asbestos removal has high automation potential for as an example on the social part. So it's risk reduction for health for workers and residents, but also on the economic part, which is an early return of investment because the use case and the actual process is cost intensive. So the return of investment for cost intensive robots could become even further than in normal renovation use cases. And technologically, we see that the construction sites are well structured in relative position, but for refurbishment, it's quite clear, and tasks are highly repetitive. And when we look onto the process, how it's done manually at the moment, so often it started with taking samples, they are analyzed, and afterwards, the entire building is secluded, and then starts the manual process of execution. So you see humans are covered in plastic suits so that they don't get into contact with the hazardous material, and especially not with the created dust. But as you might also consider, it is a challenging task to keep humans completely safe in these environments. So after having everything removed, the environment is measured. If still asbestos is retained in the building, afterwards the deposit is in special waste bags. And yeah, this is the current process that we have. And you see, I have drawn this blue arrow in the blue rectangle in the center. The idea is that we exactly move over in this direction, that we tackle the manual work in the center to introduce automated construction for this. So when we look into this, we decided to go for a test-driven design approach. Why do we choose it? So we started with market analysis and all the background tests, and we found out that we are not able to set all the requirements that are necessary for truly designing the system. So what we did is having a first prototype very, very, very early in the process. So after 1 year, we had this one here and started testing it to the bottom of its heart, just to understand how do we specify requirements in the details. And as you also see, the system architecture changed a lot due to the second prototype. And also this one was tested in the end to the bottom of its heart. And I will just now go into some key findings that we made during switching from first prototype to second prototype. As you see here, the first prototype was integrating all the essential parts. So especially the red one here, aspiration, is essential for our discussion now, because the aspiration system is collecting all the dust created by the tool at the end effector and is creating the bags of disposal. We found out, and you see this one here. So this is one of our early grinding tests. This is after 10 seconds, you don't see the problem. But when I slip forward, you see this is 2 minutes. And when I go into 4 minutes, we have a dust problem. So the size of the aspiration wasn't be possible to take all the dust. So in the end, this was by a rate of 80%, but 20% of asbestos was not aspirated, and this is a critical safety issue. So we decided to change the entire architecture of the system so that aspiration becomes centralized. And this is the case here. So we can oversize it to our own needs, which was a step change in our architecture, but really necessary. But as you also see, we somehow need to handle the hose for getting the suction power from the tool out of the seclusion to the aspiration system. And this led by us to this coupled tandem solution and collecting all the key findings. So aspiration is not possible to be on the robot. Waste handling is very complex. Centralizing the aspiration system is required, but also takes hose handling as required. And this was the reason why we split into tandem. Continuing with some insights. So we started with mobile basis differential drive because we needed to have it very lightweight and easy. And this was the easiest solution that we saw because the non-holonomic movement of the differential drive for a single robot was totally fine. Going to the second prototype, having a coupled tandem, differential drive wasn't sufficient anymore. So we had to change to Mecanum wheels and a holonomic movement. And what you see here is that it is quite nice when you go into the movement of coupled mobile bases. So now you have the freedom to also operate in tight corners and tight edges to get this solved. And key findings were removal robot at the same would be able to go with both drive concepts, but changing to the tandem, we need to have holonomic movement. Talking about the manipulators, they were both self-solutions because the requirements were too hard for industrial manipulators. So in the end, we had to design them on ourselves. What you see in a difference is, I just want to point it out here, we have a prismatic joint here and the normal 6 revolute joints afterwards. And what I extra splitted the degree of freedom because we just used the prismatic one for having an extension of the workspace, but the normal execution was done by this 6 degree of freedom. Over time, we changed it to the 7 degree of freedom solution, so 7 times revolute joints. So not possible to just write one alone, but we had some nice advantage of this. So we raised the complexity for engineering, but we could, for example, reduce the distance between the robot and the wall, because now the arm was able to fold much smaller into this space. And this for us was a big change because then we could also work in tight corners and tight corridors. And in the end, the process itself, 6 degree of freedom is fine, but the system and the context around it, that required 7 degrees of freedom. Going into the last part, oh, sorry that this video is on this part. So we do have 4 different types of end effectors solved, which is basically a solution between compliant and non-compliant solutions. I'll just go through it as a simple idea. So what you see here is we try to keep things as simple as possible, which for us means that we go into position and velocity control for our manipulator. And what you see here is this is a 3 degree of freedom compliant tool, which means they are spring loaded and the tool is self-aligning due to some freedom towards the wall. And this is what you see when we start approaching the wall, and now here it's having this angle. The next one here in the center is reducing the compliant freedom. So there's only one. When you see the video over time, you see here one normalized degree of freedom, so only one prismatic joint, normal to the surface of the tool, which is quite a nice solution for going into the position and force control. but you have a hybrid control strategy that you can still execute with some tweaks around to keep in position control for the manipulator. What we also tested is going for a straight solution, so totally rigid. You see the solution is very nice that it also adopts to non-flat areas. In the end, this was very, very difficult to follow because this requires force torque control of the manipulator. And in the end, developing this is a very challenging task. So over time, we decided to go for this 1 degree of freedom compliant tool with one additional force torque sensor. And this is already my last slide. So Thomas, don't get nervous. I know I'm over time. The final process is like this. So we keep the manual one. We have a digitized solution for getting the environment and its map. But afterwards, we start to bring the robots on site, having here the center of execution all robotized, and in the end, the manual process in the end. And if you have interests about details of this project, we do have open access book, and you have free access. And if you're interested, I'm happy to introduce you to download.